Look up at the night sky. What you see is just a fraction of the universe's story. The stars, the galaxies, even the vast cosmic web stretching across the void, they're all dancing to an invisible tune. Because here's the startling truth. Most of the universe's mass isn't in those glittering lights. It's hidden in the shadows, a ghostly presence we can't see, touch, or directly detect. This is the mystery of dark matter, a puzzle that has baffled scientists for decades, yet holds the key to understanding everything from the birth of galaxies to the fate of the cosmos itself. Think about that for a moment. Everything we've ever observed, planets, black holes, even the dust between the stars, accounts for less than 20% of the universe's total matter. The rest, it's out there, invisible, weaving through space like a silent architect, shaping the universe in ways we're only beginning to grasp. And the wildest part, we still don't know what it actually is. Is it a sea of undiscovered particles, a ripple in the fabric of space-time, or something even stranger beyond the limits of our current physics? That's where the adventure begins. Today, we're diving into 20 revolutionary theories that could finally crack this cosmic code. From ghostly WIMP to hidden dimensions, from primordial black holes to galaxies that might not need dark matter at all, these ideas aren't just science fiction. They're the cutting edge of human curiosity, the boldest attempts to explain the unexplainable. Some might sound unbelievable, others could rewrite the laws of physics as we know them. But one thing's certain, each theory opens a door to a universe far stranger, far more wondrous than we ever imagined. So buckle up. By the end of this journey, you'll never look at the night sky the same way again. If dark matter were a cosmic detective story, WIMP would be the prime suspect. These shadowy particles, short for weakly interacting massive particles, are like the universe's ultimate introverts. They barely say hello to ordinary matter, passing through stars, planets, and even your body without leaving a trace. Yet their sheer numbers could explain why galaxies spin faster than they should, or why clusters of galaxies bend light like a funhouse mirror. Picture this: trillions of WIMP might be streaming through you right now, each one 1,000,000 times heavier than an electron, yet so ghostly they rarely bump into atoms. That's why scientists have turned the hunt into a high-stakes game of hide and seek. In abandoned mines and deep underground labs, ultra-sensitive detectors wait in icy darkness, shielded from cosmic rays, hoping to catch the faintest whisper of a WIMP collision. But here's the twist: after decades of searching, we've found nothing, not a single confirmed signal. Some experiments saw tantalizing flickers, like the controversial Dama project in Italy, which claimed seasonal WIMP fluctuations. Others, like the ultra-precise LUX Zeppelin detector, came up empty. This cosmic silence has left physicists scratching their heads. Are WIMP just too shy, or are we looking in the wrong place entirely? The mystery deepens when you consider alternative ideas. Maybe WIMP aren't one type of particle but a whole family, each with different quirks. Or perhaps they interact through forces we haven't discovered yet, slipping past our detectors like thieves in the night. One thing's clear: if WIMP are out there, they're playing hard to get, and that only makes the hunt more thrilling. So where does this leave us? WIMP remain a brilliant theory, elegant in their simplicity, but the universe loves throwing curveballs. Whether they're the answer or just a stepping stone to something stranger, the search for these phantom particles has already reshaped how we see the cosmos. And who knows, the next breakthrough might be lurking in the data, waiting for someone to connect the dots. While WIMP dominate the dark matter conversation, there's another contender hiding in the quantum shadows, one so light it barely registers as a whisper in the cosmos. Meet Axions, hypothetical particles so tiny they make electrons look like sumo wrestlers. Born from an elegant solution to a puzzle in particle physics, these featherweight candidates could rewrite the dark matter playbook entirely. Unlike their bulky WIMP cousins, Axions wouldn't lumber through space as discrete particles. Instead, they'd behave more like an ocean wave, a shimmering, invisible tide washing through the universe. Picture ripples on a pond, but stretched across billions of light years, gently tugging at galaxies without ever making a splash. This wave-like nature means Axions could be everywhere at once, filling the cosmos with a delicate quantum hum. The hunt for these ethereal particles is just as creative as the theory itself. Scientists are repurposing some of the most powerful magnets on Earth, turning them into cosmic fishing nets. Inside devices like the Axion Dark Matter Experiment, or ADMX, superconducting magnets create intense magnetic fields, hoping to coax an action into revealing itself by converting into a faint microwave photon. It's like listening for a single note in a symphony of static, a needle in a haystack made of needles. But here's where it gets even wilder. If Axions exist, they might not just explain dark matter. They could be the universe's original timekeepers. Some theories suggest these particles formed in the first trillionth of a second after the Big Bang, freezing into the cosmic fabric like echoes of creation. Their presence could even solve lingering mysteries in quantum mechanics, bridging gaps in our understanding of how forces like electromagnetism work at the smallest scales. Of course, the challenge is catching something that barely interacts with reality. Axions are so elusive that even sunlight passing through a brick wall has more impact than a swarm of these particles. Yet their potential is too tantalizing to ignore. Recent upgrades to detectors have brought us closer than ever, with some experiments now sensitive enough to hear the equivalent of a single raindrop falling in a thunderstorm. So are Axions the missing piece of the dark matter puzzle? They're certainly leading one of the most fascinating chapters in modern physics. Whether they're the answer or just another clue in a deeper mystery, their story reminds us that sometimes the universe's biggest secrets come in the smallest packages. And if we do find them, it might not just solve a cosmic riddle. It could open a whole new window into how reality itself works. Imagine a universe so young that stars hadn't even flickered to life yet, a seething, chaotic place where space itself was a turbulent ocean of energy. In that primordial soup, tiny knots of matter might have collapsed under their own gravity, forming black holes no wider than an atom but as heavy as a mountain. These aren't the monstrous black holes we know today, born from dying stars. These would be relics of creation itself, hiding in plain sight for billions of years. And if they exist, they could rewrite the dark matter story entirely. This is the daring idea behind primordial black holes. Forget particles. What if dark matter is actually a cosmic swarm of these ancient gravitational traps? Think of them as invisible pebbles strewn across the universe, so small they'd zip through planets without a trace, yet collectively massive enough to bend galaxies into shape. Their sheer numbers could explain why we see the gravitational effects of dark matter but can't detect its source. The hunt for these phantom black holes is as clever as the theory itself. Scientists are turning to gravitational wave detectors like LIGO and Virgo, listening for the faintest ripples in space-time that might betray their presence. When two primordial black holes collide, they'd send out a whisper of gravitational waves, a signature far quieter than the crashes of stellar black holes, but potentially detectable with next-generation instruments. Some researchers even scour the night sky for mysterious flashes of light, watching for moments when one of these tiny black holes might magnify a distant star's light like a cosmic magnifying glass, a phenomenon called microlensing. But here's where things get even more intriguing. Primordial black holes could solve more than just the dark matter puzzle. Some theories suggest they might be the seeds of supermassive black holes lurking at the hearts of galaxies, objects so enormous they shouldn't have had time to grow so big in the universe's lifespan. Others speculate they could be behind bizarre cosmic events, like unexpected bursts of radiation, or even the legendary Planet Nine's gravitational tug in our own solar system. Of course, not everyone's convinced. Critics point out that if primordial black holes were everywhere, we'd expect to see more evidence, more microlensing events, more gravitational wave chirps. Yet the absence of definitive proof hasn't killed the idea. Instead, it's sparked creativity. Maybe these black holes cluster in halos around galaxies, avoiding detection. Or perhaps they're not all the same size, with some evaporating over time due to Hawking radiation, leaving behind only the heaviest survivors. Whether primordial black holes are the answer or just another fascinating detour in the dark matter quest, one thing's certain: they force us to rethink the boundaries of physics itself. If confirmed, they'd be a living fossil from the universe's first moments, a direct window into a time before time, and that's a revelation worth waiting for. What if we've been asking the wrong question all along? Instead of hunting for invisible particles, maybe the real mystery lies in gravity itself. That's the radical proposition of modified Newtonian dynamics, or MoND, a theory that tosses dark matter aside and rewrites the rules of how gravity works. At its core, MoND suggests that Newton's famous laws, which work flawlessly here on Earth, might need a cosmic upgrade when applied to the vast emptiness between stars. Think of it like this: gravity as we know it is a familiar song, predictable and steady. But in the outskirts of galaxies where stars whirl at impossible speeds, MoND proposes the music changes. The gravitational pull strengthens just enough to explain those spinning stars without invoking dark matter's shadowy embrace. It's as if the universe has a hidden volume knob for gravity, turning it up where the darkness feels emptiest. The beauty of MoND lies in its simplicity. No exotic particles, no invisible halos, just a subtle tweak to the equations that have governed physics for centuries. When applied to individual galaxies, the theory works startlingly well. Spiral galaxies with their graceful arms, dwarf galaxies drifting in isolation. Their rotations align almost perfectly with MoND predictions. It's a rare moment in science where elegance meets explanatory power, but here's where the cracks appear. While MoND dances gracefully with single galaxies, it stumbles when faced with the broader cosmos. Galaxy clusters, those massive metropolises of stars and gas, still seem to demand some unseen mass to explain their gravitational grip. Even more damning, the eerie patterns of light bending around these clusters, a phenomenon called gravitational lensing, point to far more distortion than MoND can easily account for. Supporters aren't ready to concede, though. Some propose extensions to the theory, adding layers of complexity to bridge these gaps. Others argue we're missing a crucial piece of the puzzle, like how Einstein's relativity once refined Newton's work. Could MoND be the first hint of a deeper gravitational truth, one that transcends both Newton and dark matter? The debate cuts to the heart of how science progresses. Do we cling to the comfort of invisible matter we've yet to find, or dare to rewrite the laws that have guided us for generations? MoND may not have all the answers, but its very existence challenges us to question assumptions, and in that rebellion, it's already reshaped the conversation. Whether it's ultimately right or wrong, one thing's certain: the universe still has surprises up its sleeve. Neutrinos are already some of the most elusive particles in existence, ghostly cosmic travelers that stream through matter as if it weren't even there. But what if there's an even stranger version of these particles, one so stealthy it makes ordinary neutrinos seem downright sociable? enter sterile neutrinos, a hypothetical heavyweight cousin that could be hiding in plain sight as dark matter. Unlike the neutrinos, we know particles that at least occasionally bump into atoms via the weak nuclear force. Sterile neutrinos would interact with the universe through gravity alone. Picture a particle so aloof it ignores every fundamental force except the faintest tug of spacetime itself. That's why spotting one would be like trying to catch smoke with your bare hands. Yet if they exist, their sheer mass could solve two puzzles at once: the missing matter holding galaxies together and the mysterious excess of high-energy neutrinos detected in experiments like Mini Bose and LSD. The hunt for these phantom particles takes scientists to some of the most extreme environments on Earth and beyond. Deep underground, detectors filled with liquid argon or xenon watch for telltale flashes of light, anomalies in neutrino behavior that might hint at sterile neutrinos oscillating in and out of existence. Meanwhile, orbiting telescopes like NASA Chandra X-ray Observatory scan distant galaxies for unexplained X-ray emissions, which could be the death throes of sterile neutrinos decaying after billions of years. Even the cosmic microwave background, the afterglow of the Big Bang, might hold clues in subtle distortions that point to these particles' gravitational fingerprint. Here's where it gets truly mind-bending. If sterile neutrinos are real, they could be cosmic shape-shifters. Some theories suggest they might briefly activate into regular neutrinos before vanishing again, like a shadow flickering in and out of reality. Others propose they're the reason certain galaxies appear oddly lacking in dark matter, perhaps because sterile neutrinos clustered differently in the early universe, leaving voids where we'd expect darkness to dominate. Critics argue the evidence is still too shaky, with conflicting results from different experiments leaving the field in limbo. But that uncertainty is exactly what makes sterile neutrinos so tantalizing. They exist at the edge of our understanding, a reminder that the universe's rulebook might have chapters we haven't even glimpsed yet. Whether they're the key to dark matter or just another piece of the puzzle, their story forces us to rethink what's possible, and that's how breakthroughs are born. What if dark matter isn't just hiding in the shadows? What if it's whispering to itself in a language we can't hear? That's the spine-tingling possibility behind dark photons, hypothetical messengers that could be carrying signals through a secret cosmic backchannel. Picture this: while our universe buzzes with familiar forces like electromagnetism, there might be an entire shadow realm operating under its own set of rules, with dark photons as its invisible telegraph wires. These aren't your everyday particles. Dark photons would be the glue holding dark matter together, mediating interactions in a hidden sector of reality, one where particles we've never seen dance to the tune of forces we've never felt. Imagine two parallel cities built on the same land, one bustling with light and sound, the other silent and unseen, yet both shaping the same space. That's the scale of what dark photons imply. If they exist, they'd be the first tangible bridge between our world and this elusive dark universe. The hunt for these phantom force carriers is already underway in some of the world's most advanced labs. Experiments like the Dark SRF project at Fermi National Accelerator Laboratory are tuning particle beams with laser-like precision, searching for anomalies where energy seems to vanish, potential evidence of dark photons stealing momentum into their hidden dimension. Others, like CERN NOS 64, smash electrons into targets, watching for telltale gaps in the debris that might betray a dark photon's fleeting appearance. Even household appliances aren't off the table. Some researchers repurpose old microwave cavities, turning them into traps for these hypothetical particles. But here's where the plot thickens. Dark photons might not just be messengers, they could be shape-shifters. Some theories suggest they occasionally mix with ordinary photons, briefly flickering into our reality like a radio picking up a distant station. This could explain baffling experimental results, like the anomalous magnetic moment of muons, where particles behave slightly differently than predicted. If dark photons are the culprits, they'd be leaving fingerprints all over physics without us realizing it. Yet the implications stretch far beyond particle detectors. If dark photons are real, they could solve one of dark matter's biggest puzzles: why it clumps so perfectly around galaxies. Ordinary matter interacts and collides, but dark matter seems to glide smoothly, forming vast halos. Dark photons could provide the gentle push needed to keep dark matter particles just the right distance apart, a cosmic choreography where the dancers never touch. Of course, skeptics point out we haven't caught one yet. But absence of evidence isn't evidence of absence, especially when hunting something that by definition avoids detection. Every null result narrows the possibilities, inching us closer to either a breakthrough or a revolution in how we search. Whether dark photons are the key to the dark universe or just another stepping stone, their very possibility reminds us how much of reality might still be waiting in the wings, hidden but not forever. Supersymmetry is the kind of idea that makes physicists giddy, a mathematical symphony so beautiful it feels like uncovering the universe's hidden blueprint. At its heart lies a simple yet profound notion. For every particle we know, from the humble electron to the flamboyant Higgs boson, there exists a secret twin. These superpartners would be heavier, more elusive versions of their ordinary counterparts, like cosmic doppelgangers hiding just beyond our reach. And here's the kicker: the lightest of these twins could be the very stuff of dark matter, drifting unseen through the cosmos. Think of it as the universe's ultimate balancing act. Supersymmetry, or SUSY for short, emerged as a way to tidy up some of physics' messiest problems. It explains why the Higgs boson is surprisingly lightweight compared to theoretical predictions, and it elegantly unites the fundamental forces under one mathematical roof. But its most tantalizing gift might be dark matter candidates like the Neutrino, a hypothetical superpartner that doesn't interact with light, doesn't clump like ordinary matter, and could be floating through your body right now by the billions. The hunt for these phantom particles has turned the Large Hadron Collider into a cosmic detective. Buried beneath the Swiss-French border, this 17-mile ring of supercooled magnets smashes protons together at nearly the speed of light, recreating conditions not seen since the universe's first trillionth of a second. Scientists hoped SUSY particles would reveal themselves in the debris, their hefty mass leaving unmistakable fingerprints in the data. Yet after years of collisions, the LHC has come up empty. No neutralinos, no squarks, no gluinos. Just eerie silence where theorists expected a fireworks display. This absence doesn't mean supersymmetry is dead, though. Some researchers argue we've been looking in the wrong energy range, or that superparticles are even more elusive than predicted. Others propose stealth SUSY models, where these particles decay in ways that leave almost no trace. There's also the spine-tingling possibility that the LHC did produce superparticles, but they slipped through our detectors like ghosts through walls, unnoticed because they barely interact with ordinary matter. What keeps SUSY alive is its sheer explanatory power. Without it, the Higgs boson's mass becomes a cosmic coincidence, and the unification of forces crumbles into a patchwork of loose ends. Even if the LHC never finds proof, supersymmetry's elegance ensures it will inspire theorists for decades. After all, the universe has a habit of being stranger than we imagine, and sometimes the most beautiful ideas just take longer to confirm. Whether SUSY is the final answer or a stepping stone to something even grander, its legacy is already etched into the quest to understand the cosmos. And who knows, the next collision, the next detector upgrade, might finally reveal the superpartners we've been dreaming of. At the smallest scales of the universe, where spacetime itself seems to froth and bubble like a quantum sea, lies a startling possibility. What if dark matter isn't made of particles at all? Imagine gravity not as the smooth curve Einstein described, but as a shimmering tapestry of tiny, discrete threads. These quantum knots in the fabric of reality could be the hidden architects of the cosmos, their collective weight bending galaxies into shape without a single exotic particle in sight. This is the wild frontier of quantum gravity dark matter, where the rules of the very small might solve the mysteries of the very large. In theories like loop quantum gravity or string theory, spacetime isn't continuous, it's pixelated, built from indivisible units far smaller than an atom. On human scales, this granularity is invisible, like trying to spot the individual grains of sand that make up a beach, but stretch across light years, and these quantum fluctuations could add up to something monumental, a cosmic shadow mass woven into the universe's very structure. Picture a galaxy not as a collection of stars held together by invisible matter, but as a whirlpool in this quantum foam. The turbulence at spacetime's smallest scales might create subtle gravitational echoes, tiny eddies that amplify into the effects we attribute to dark matter. It's as if the universe has been playing a trick on us all along. The missing mass was never missing. It was hiding in plain sight, encoded in the geometry of reality itself. The implications are dizzying. If quantum gravity dark matter is real, it would bridge two of physics' greatest puzzles, the nature of dark matter and the quest to unify quantum mechanics with general relativity. Experiments like the Laser Interferometer Gravitational Wave Observatory, or LIGO, might already hold clues. Gravitational waves from colliding black holes could carry faint imprints of spacetime's granularity, whispers of a deeper structure beneath the smooth equations we use today. Even the cosmic microwave background, that ancient afterglow of the Big Bang, might bear scars from these quantum ripples frozen in time, yet the road ahead is thorny. Unlike particle-based theories, quantum gravity dark matter leaves no obvious trail for detectors to catch. You can't trap a spacetime fluctuation in a lab or watch it decay in a collider. Proving this idea would require rethinking how we observe the universe itself, perhaps by measuring how light bends around galaxies with unprecedented precision, or hunting for subtle anomalies in the orbits of distant stars. Some theorists even propose that black holes, those ultimate spacetime warps, could act as cosmic magnifying glasses, revealing quantum gravity's fingerprints in their violent mergers. Skeptics argue the math is still too fuzzy, the evidence too indirect, but that's the thrill of frontier science. Sometimes the craziest ideas turn out to be true. Whether quantum gravity dark matter holds up or not, it forces us to ask deeper questions. What if dark matter isn't something we've overlooked, but something we've misunderstood all along? The answer might not lie in the shadows of the cosmos, but in the shimmering quantum depths of spacetime itself. And that's a revelation worth chasing, no matter how elusive the truth may be. Imagine waking up one morning and discovering your reflection isn't just a trick of the light. It's an entire parallel world, invisible yet just as real as your own. This isn't science fiction, it's the mind-bending premise of mirror matter, a theory suggesting our universe has a hidden twin where particles, forces, and even planets might exist in perfect symmetry with ours. But here's the twist. These mirror versions of reality don't interact with us through light or electromagnetism. They're bound to our world by gravity alone, making them the ultimate cosmic ghosts and the perfect candidate for dark matter. Picture a universe where every electron, every quark, every star has a mirror counterpart. In this shadow realm, the laws of physics might look eerily familiar, but with subtle differences. Perhaps mirror protons are slightly heavier, or mirror atoms form exotic structures unlike anything we've seen. The two universes would coexist in the same space, overlapping like layers of a hologram, yet oblivious to each other's presence. When you wave your hand, trillions of mirror particles stream right through it, leaving no trace except the faintest gravitational tug. The idea isn't as far-fetched as it sounds. Physicists have long noticed strange symmetries in nature, like how every particle has an antimatter twin. Mirror matter takes this elegance a step further, proposing an entire hidden sector of reality. Some theories even suggest that the Big Bang didn't just create our universe, it spawned two, locked in a gravitational embrace. Over billions of years, mirror matter would have clumped into vast structures just like ordinary matter, forming invisible galaxies, stars, and planets that weave through ours unseen. Hunting for this cosmic doppelganger requires ingenious detective work. Scientists scour neutron stars for anomalies. These ultra-dense objects might occasionally capture mirror particles, heating up in ways that defy explanation. Others analyze the cosmic microwave background for odd patterns, hunting for gravitational imprints of mirror galaxies brushing against ours. Even underground experiments like the Ice Cube Neutrino Observatory in Antarctica watch for rare collisions where ordinary and mirror particles might briefly interact, leaving behind a telltale burst of energy. But the most tantalizing clue might lie in our own solar system. Some researchers speculate that mirror matter could explain the perplexing orbits of distant objects beyond Neptune, like the hypothetical planet 9. If a mirror world, let's say, a mirror Earth or Mars floats unseen in our cosmic neighborhood, its gravity could nudge icy bodies into strange trajectories without ever revealing itself directly. Of course, skeptics argue mirror matter is a solution in search of a problem, an elegant idea without definitive proof. Yet its allure is undeniable. Unlike other dark matter candidates, mirror matter offers a grand unification, an entire shadow universe with its own rich physics waiting to be discovered. Whether it's real or not, the theory stretches our imagination, forcing us to confront a humbling possibility that everything we see, everything we know, might just be half the story. And if that's true, the cosmos just got infinitely more interesting. For decades, we've pictured dark matter as a cosmic loner, particles drifting silently through space, indifferent to everything, even each other. But what if that's not the whole story? Imagine dark matter not as a solitary ghost, but as a bustling, invisible society, with particles that collide, scatter, and maybe even form intricate structures we can't see. This is the radical idea behind self-interacting dark matter, a theory that turns the conventional view on its head and paints the cosmos in far more dynamic shades. The clues hiding in plain sight come from some of the universe's most violent events: galaxy collisions. When two galactic clusters smash together, their dark matter should behave like a swarm of transparent bullets, passing through one another without a fuss. But something odd happens in places like the Bullet Cluster, where telescopes captured the aftermath of such a cosmic wreck. The visible gas, hot and glowing, slowed down as expected, but the dark matter traced by its gravitational lensing effect seemed to lag behind in a way that defies the loner model. It's as if the dark matter particles hesitated, like dancers briefly brushing against each other before moving on. This subtle hesitation hints at a hidden richness. If dark matter particles interact, even weakly, they could be doing far more than just hovering in space. They might form invisible disks, clump into dense halos, or even generate dark weather patterns of movement and density fluctuations within galaxies. Picture an entire shadow ecosystem with currents and eddies flowing through the cosmos. sculpting the distribution of galaxies in ways we're only beginning to map. Some simulations even suggest self-interacting dark matter could explain why small galaxies have such diffuse halos. Perhaps collisions between dark particles smooth them out over billions of years. Yet the theory isn't without its skeptics. If dark matter interacts strongly, why don't we see more dramatic evidence? Where are the smoking gun signatures, like dark matter piling up in the cores of galaxies instead of spreading out? Proponents counter that the interactions might be rare or dependent on conditions we haven't accounted for, like a hidden force that only kicks in at certain energies. Others propose that dark matter might have multiple flavors, with some particles interacting while others remain aloof, creating a mix of behaviors that's devilishly hard to untangle. The implications stretch beyond astrophysics. If dark matter has its own social dynamics, it could mean there's a whole dark chemistry waiting to be discovered, rules governing how these particles bond, repel, or exchange energy. Are there dark atoms, dark molecules? The possibilities ignite the imagination, suggesting a cosmos far more layered than we ever dreamed. For now, the hunt continues. Telescopes like the James Webb Space Telescope peer deeper into colliding galaxies, while underground detectors refine their sensitivity to any hint of dark matter's secrets. Whether self-interacting dark matter holds up or not, it's already reshaped the conversation, proving that even the most elusive stuff in the universe might have a story to tell. And if we're right, that story could be as complex and vibrant as the visible cosmos we call home. Picture the universe not as a collection of discrete particles, but as an ocean, a vast, rippling expanse where matter isn't solid but fluid, swirling in wave-like patterns we've barely begun to map. This is the essence of fuzzy dark matter, a theory that swaps traditional particle models for something far stranger. Dark matter so lightweight it behaves less like a bullet and more like a whisper, spreading across galaxies in a delicate quantum haze. At the heart of this idea lies a simple but radical shift. Instead of WIMP or Axions, fuzzy dark matter proposes particles with masses a billionth of an electron's weight, so insubstantial that their quantum nature dominates. On cosmic scales, these particles wouldn't clump like sand. They'd ripple like sound waves, forming interference patterns that sculpt the universe's hidden scaffolding. Think of it as cosmic jazz, where the notes aren't particles but vibrations, harmonizing into the gravitational symphony that holds galaxies together. This could solve one of dark matter's stickiest puzzles, the missing satellites problem. Simulations based on heavy dark matter particles predict that our Milky Way should be surrounded by thousands of dwarf galaxies, like fireflies swarming a lantern. Yet we've found only a few dozen. Fuzzy dark matter offers an elegant fix those ultra-light waves would smear out on small scales, smoothing away the tiny clumps that ought to become dwarf galaxies. It's as if the universe hit a cosmic blur filter, erasing the fine-grained details while preserving the grand structure. The implications ripple outward. If fuzzy dark matter is real, galaxies might not be anchored by halos of discrete particles but by standing waves, invisible quantum crests and troughs guiding stars into their graceful spirals. Some theorists even suggest these waves could imprint faint signatures in the way galaxies rotate, like a subtle watermark hidden in their motion. Others hunt for clues in the cosmic microwave background, where the faintest unevenness might betray the interference patterns of this primordial quantum fog. Yet challenges remain. How do you detect something with so little mass it barely registers as matter? Traditional detectors, built to catch rare particle collisions, would be useless here. Instead, scientists turn to the cosmos itself as their laboratory. precision measurements of starlight bending around galaxies could reveal the telltale softness of a wave-like dark matter medium. Pulsars, those ultra-precise cosmic lighthouses, might flicker in ways that betray the passage of dark matter waves. Even the delicate dance of binary black holes could carry echoes of this quantum fluid's presence. Skeptics argue the theory stretches Occam's razor, trading one mystery for another. But sometimes the universe demands we think outside the box, or in this case, outside the particle. Whether fuzzy dark matter holds up or not, it reminds us that reality might be far more fluid, far more interconnected than our rigid categories suggest. And if we're right, the cosmos isn't just filled with invisible matter. It's humming with an ethereal quantum melody, waiting for us to learn how to listen. Imagine dipping your hand into a river that flows without resistance, no tug of water against your skin, no swirls or eddies breaking the surface. Now scale that up to galactic proportions, and you've got the mind-bending essence of superfluid dark matter. This theory takes the familiar idea of dark matter halos and gives it a quantum twist, proposing that the invisible glue holding galaxies together isn't made of sluggish particles, but of an ultra-cold, frictionless liquid that defies everything we know about physics. At temperatures near absolute zero, certain materials like liquid helium here on Earth become superfluids, losing all viscosity and flowing endlessly without losing energy. Apply that behavior to dark matter, and suddenly the motions of galaxies snap into focus. A superfluid halo would naturally explain why stars at the edges of spiral galaxies rotate faster than expected. The dark matter isn't just sitting there passively, but swirling in a quantum dance, its collective motion creating the extra gravitational pull we observe. It's like an invisible carousel, with the superfluid's rotation subtly tugging stars along for the ride. But how could something so delicate, so easily disrupted by heat or turbulence, persist across the cosmos? Proponents argue that in the near-perfect vacuum of space, dark matter could remain cold enough to maintain its superfluid state for billions of years. Some models even suggest this fluid isn't entirely silent. It might vibrate at specific frequencies, generating faint gravitational waves that ripple through space-time like the aftertones of a cosmic bell. The implications get wilder when you consider how this superfluid might interact with gravity itself. In some theories, the fluid's quantum properties could slightly alter the force of gravity in ways that mimic modified Newtonian dynamics, bridging the gap between particle-based and gravity-altering dark matter models. Picture a galaxy not as an island in empty space, but as a whirlpool in this unseen quantum ocean, its shape and motion sculpted by fluid dynamics we're only beginning to fathom. Yet challenges loom. If dark matter is a superfluid, why don't we see more dramatic effects in colliding galaxies, where the fluid should slosh and splash in detectable ways? And how does it clump enough to form the intricate cosmic web we observe? Some theorists propose a hybrid approach. Maybe most dark matter behaves like a superfluid, but with a sprinkling of traditional particles mixed in, creating a blend that explains all the observations. The hunt for answers is as creative as the theory itself. Scientists are re-examining data from gravitational wave detectors, searching for hints of superfluid vibrations. Others simulate galaxy formation with fluid dynamics algorithms, watching to see if virtual superfluid halos reproduce the real universe's structure. And lurking in the background is a tantalizing question. If dark matter flows like a liquid, could it ever form droplets, waves, or even quantum vortices, structures so strange they'd rewrite the textbook on cosmic evolution? Whether superfluid dark matter holds up or not, it's a dazzling reminder that the universe's secrets might not lie in rigid particles or static forces. but in the graceful, ever-moving rhythms of a hidden quantum sea. And if we're right, the cosmos isn't just filled with invisible matter, it's alive with an elegance we're only starting to perceive. What if dark matter isn't eternal? The cosmic scaffolding holding galaxies together might be slowly unraveling, particle by particle, in a silent decay we've only just begun to suspect. This is the provocative premise of decaying dark matter, a theory that suggests the universe's hidden mass isn't just sitting idly in the shadows, but gradually transforming into something else, emitting faint whispers of radiation across the cosmos. Picture a block of ice sublimating in sunlight, vanishing molecule by molecule without leaving a puddle. Now imagine that same process playing out on a galactic scale, with dark matter particles dissolving over billions of years into lighter particles or even bursts of energy. Unlike the sudden flash of a supernova, this decay would be achingly slow, a cosmic hourglass where the sand trickles so gradually, entire civilizations could rise and fall between each grain. Yet over the eons, even this faint leakage could leave fingerprints in the fabric of space. Astronomers are already scanning the skies for these ghostly signatures. When dark matter decays, some models predict it could release photons in the X-ray or gamma-ray spectrum, invisible to our eyes but detectable by telescopes like NASA Chandra or the European Space Agency's XMM Newton. In 2014, researchers studying 73 galaxy clusters spotted an unexplained X-ray emission at around 3.5 kiloelectronvolts, a spike that defied conventional explanations. Could this be the death rattle of dark matter particles, shedding energy as they fade from existence? The signal remains controversial, but it's a tantalizing hint that the universe's shadows might not be as static as we thought. The implications ripple far beyond a single anomalous reading. If dark matter decays, it could solve lingering mysteries about how galaxies evolve. Young, energetic galaxies might have started with thicker dark matter halos that thinned over time like a fading echo. Dwarf galaxies, which seem to have less dark matter than expected, might simply be further along in this slow-motion evaporation. Even the cosmic web, the vast, filamentary structure of the universe, could bear scars from dark matter's gradual retreat, like tide marks on a cosmic shoreline. Yet not all decay models paint the same picture. Some theories propose dark matter breaks down into ordinary neutrinos, leaving no electromagnetic trace at all. Others suggest it might cascade through multiple exotic particles, creating a spectrum of secondary signatures. The most mind-bending versions involve asymmetric decay, where dark matter particles and their antiparticles disintegrate at different rates, potentially leaving behind a residue that fuels future cosmic structures. Skeptics argue these ideas stretch Occam's razor. Why complicate dark matter when simpler models suffice? But the universe has never been shy about complexity. After all, radioactivity was once dismissed as impossible until Marie Curie proved otherwise. If dark matter is indeed decaying, the consequences would be profound. It would mean the universe's hidden architecture is dynamic, evolving in ways we're only beginning to grasp, and that realization could rewrite not just the story of dark matter, but the ultimate fate of everything. Because if even the shadows aren't permanent, what else might be changing right under our noses, or rather, right through them? What if dark matter isn't just hiding in the shadows of our universe? What if it's lurking in the very fabric of reality itself, tucked into dimensions we can't see or touch? This is the spine-tingling possibility that extra dimensions bring to the dark matter mystery. According to string theory, the universe might not be limited to the 3 spatial dimensions we experience every day. Instead, it could be a vast, multidimensional landscape with hidden layers folded so tightly they're invisible to us, like a sheet of paper viewed edge on. And here's the kicker, dark matter might not be missing at all. It could be right beside us, just one dimension over, silently shaping the cosmos from beyond our perception. Imagine a world where gravity isn't confined to our familiar 3 dimensions. In higher dimensional space, it could spread out like ripples in a pond, weakening as it filters into our reality. But dark matter particles, if they're native to these extra dimensions, might feel gravity's full force, explaining why they seem to have such a strong gravitational grip without interacting with light or matter. It's like listening to an orchestra play behind a thick curtain. You hear the music, but the musicians remain unseen. The math behind this idea is as elegant as it is mind-bending. In some string theory models, particles like the hypothetical Kaluza-Klein photon could be the bridge between dimensions, carrying gravity's influence while remaining invisible to our detectors. These higher dimensional dark matter candidates wouldn't just be hiding, they'd be fundamentally unreachable through any force except gravity. That's why our most sensitive experiments, designed to catch particle collisions or rare interactions, keep coming up empty. We're fishing in a 3-dimensional pond, while the real catch might be swimming in waters we can't even access. But how do you search for something that exists outside your perception? Scientists are getting creative. Particle colliders like the Large Hadron Collider might produce telltale energy gaps in their data, missing momentum that could hint at particles darting into extra dimensions. Gravitational wave detectors, too, could spot anomalies in the way black holes merge, subtle distortions that betray the influence of unseen dimensions. Even the cosmic microwave background might hold clues, its faint imperfections possibly encoding the gravitational whispers of higher dimensional matter. Skeptics argue that extra dimensions are a convenient mathematical trick, a way to explain away dark matter's elusiveness without direct proof. But the universe has surprised us before. After all, no one could see atoms until we built the tools to reveal them. If extra dimensions are real, they wouldn't just solve the dark matter puzzle. They'd revolutionize our understanding of reality itself, proving that the cosmos is far stranger, far more layered than we ever dared to dream. And that's a revelation worth chasing, no matter how many dimensions it takes. Before the first true stars ignited, before galaxies spun into being, the universe might have glowed with a different kind of light, not from nuclear fusion, but from the annihilation of dark matter itself. This is the hauntingly beautiful premise of dark stars, hypothetical giants that could have dominated the cosmos in its earliest days. Picture a celestial body 1,000,000 times more massive than our Sun, radiating not with the familiar blaze of hydrogen and helium, but with an eerie, otherworldly luminescence as dark matter particles collided and annihilated at its core. These wouldn't be stars as we know them. Instead of fighting gravity with the outward pressure of nuclear reactions, dark stars would balance their immense weight through the constant energy release of dark matter annihilation. The result, a colossal, diffuse sphere, cooler than conventional stars but unimaginably vast. Some models suggest they could have stretched across entire solar systems, their faint glow visible across the young universe. Their existence would solve several cosmic puzzles, including unexpected signatures in the infrared background radiation that telescopes like the James Webb Space Telescope are now scrutinizing. The formation process would have been unlike anything in modern astrophysics. In the dense, dark matter-rich environment of the early universe, pockets of ordinary gas might have collapsed around dark matter clumps. As these protostars grew, their gravitational pull would have drawn in more dark matter, creating a self-sustaining cycle of annihilation and energy release. Unlike today's stars, which eventually exhaust their fuel, dark stars could have lived for millions of years, possibly even surviving into the era when the first conventional stars began to shine. But here's where the story takes a twist. Some theories suggest these dark stars might have been the seeds for supermassive black holes. As dark matter became scarce in their cores, the stars could have collapsed under their own weight, birthing the gargantuan black holes we now find at the centers of galaxies. It's a cosmic metamorphosis that would link two of the universe's greatest mysteries, dark matter and the origins of supermassive black holes, in a single, elegant narrative. Detecting these ghostly giants is a challenge, but not impossible. Their lingering heat signatures might still whisper across the cosmos, etched into the cosmic microwave background or hidden in the faint infrared glow between galaxies. Upcoming telescopes equipped with ultra-sensitive infrared detectors could catch these echoes, revealing whether the universe's first light came not from fire, but from the shadowy embrace of dark matter's demise. Whether dark stars existed or not, their very possibility stretches our imagination, forcing us to reconsider what a star can be. In a universe where the invisible outweighs the visible, it's only fitting that the first lights might have been fueled by darkness itself, a poetic beginning to the cosmic story we're still piecing together today. Deep within the fabric of the cosmos, there might be an artifact older than stars, older than atoms, perhaps even older than time as we know it. This is the staggering possibility behind dark matter as a cosmic fossil, a frozen echo from the universe's violent infancy. If true, it means every galaxy's invisible halo isn't just hidden mass, it's a living snapshot of the moment reality itself began to take shape. Picture the universe in its first microseconds, a seething cauldron of energy so extreme that the very laws of physics were still being forged. In that primordial chaos, dark matter could have crystallized out of the frenzy like frost forming on a window, a relic of a time when forces we can't replicate ruled the cosmos. Unlike ordinary matter, which constantly recycles itself through stars and supernova, dark matter might have remained unchanged, untouched by the billions of years of cosmic evolution that followed. That would make it the ultimate time capsule, preserving clues about conditions so alien they defy imagination. The hunt for these clues takes scientists back to the drawing board of particle physics. If dark matter is a fossil, it must have been forged at energies far beyond what any collider can recreate, perhaps even beyond the reach of string theory. Some models suggest it's a survivor from an era when the fundamental forces were still unified, a leftover from when electromagnetism, the strong and weak nuclear forces, and gravity were one and the same. Others propose it's the residue of a phase transition, like cosmic dew condensing as the universe cooled, locking particles into a shadowy existence that persists to this day. But how do you study something that stopped interacting with the rest of reality almost immediately after its creation? Astronomers turn to the cosmos itself as their laboratory. The distribution of dark matter, how it clumps around galaxies, how it threads through the cosmic web, could encode details about its birth. Subtle variations in its density might reveal how it decoupled from the primordial fireball, like reading tree rings to uncover ancient climate patterns. Even the way dark matter particles move could betray their origins. If they're cold, moving sluggishly from the start, it would hint at formation in a dense, high-energy environment, while warm, dark matter might suggest a later, gentler birth. The implications stretch beyond astrophysics. If dark matter is indeed a fossil, it could resolve lingering mysteries about the Big Bang's aftermath. For instance, why does the universe have more matter than antimatter? Dark matter's properties might hold clues to that imbalance, offering a window into processes that favored the creation of everything we see and everything we don't. It might even explain why the cosmos looks so uniform on large scales, as if something smoothed it out in its earliest moments. Yet for all its promise, the fossil theory raises as many questions as it answers. If dark matter is truly primordial, why didn't it all annihilate or decay away like other exotic particles from that era? How did it survive the universe's expansion, the formation of galaxies, the relentless march of time? Some theorists propose it was protected by a symmetry principle, a cosmic law that shielded it from change. Others wonder if we're seeing only part of the picture. Perhaps dark matter did evolve, just in ways we haven't yet detected. One thing's certain, if dark matter is the universe's oldest artifact, we're not just studying the invisible scaffolding of today's cosmos. We're holding a piece of creation itself, a whisper from the moment everything began. And that makes it more than a scientific curiosity. It's a bridge to the past, waiting for us to decode its secrets. What if the universe is playing an elaborate game of cosmic charades where the dark matter we've been chasing is nothing more than a shadow cast by a reality we can't see? This is the mind-melting premise of holographic dark matter, a theory that takes one of physics' most radical ideas, the holographic principle, and turns it into a key for unlocking the universe's greatest mystery. At its heart, the holographic principle suggests something astonishing. All the information that makes up our three-dimensional universe might actually be encoded on a two-dimensional surface at its boundary, like a movie projected from the edges of reality onto the screen of spacetime. If that's true, then dark matter could be less like a particle and more like a glitch in that projection. A subtle distortion where the film of our universe doesn't quite match its source code. Picture a hologram of a rose where one petal appears darker, not because of actual pigment, but because the light projecting it is slightly skewed. That's the kind of illusion we might be dealing with on a cosmic scale. The math behind this idea is as elegant as it is bizarre. Just as a black hole's event horizon encodes all the information about what falls inside, the universe's boundary could hold the blueprint for everything within it, including the gravitational effects we attribute to dark matter. In this view, galaxies aren't being tugged by invisible mass, but by the way information is smeared across the cosmic projector. It's as if the universe is a painting where the artist left brushstrokes we can't see, only their gravitational echoes. But how do you test something so abstract? Scientists are turning to the cosmic microwave background, that ancient afterglow of the Big Bang. If dark matter is holographic, its fingerprints might appear in the way this radiation is polarized, subtle swirls and twists that reveal the universe's underlying code. Others study the large-scale structure of galaxy clusters, looking for patterns that resemble interference effects, like ripples in a pond where two stones were tossed. Even gravitational wave detectors could spot anomalies, hints that spacetime's vibrations don't quite match predictions unless you account for the hologram's hidden layers. Critics argue this is all just mathematical poetry, a beautiful idea with no concrete proof. Yet the holographic principle has already reshaped how we think about black holes and quantum gravity. If it's right about dark matter, the implications would be staggering. It would mean the cosmos is fundamentally informational, that mass and energy are secondary to the bits and codes that underpin them. The search for dark matter wouldn't just be about finding a particle, it'd be about cracking the universe's operating system. Whether holographic dark matter holds up or not, it forces us to ask a deeper question. Are we studying the universe or just its reflection? The answer might rewrite not just cosmology, but the very nature of reality itself, and that's a mystery worth projecting into the light. Time crystals sound like something ripped from a science fiction epic, structures that don't just exist in space, but pulse and repeat in time itself. These bizarre phases of matter, first theorized in 2012 and later created in labs using chilled atoms and lasers, defy the usual rules of physics. Unlike ordinary crystals with their repeating atomic patterns in space, time crystals have patterns that cycle endlessly in time, like a clock that ticks without ever being wound. Now, imagine if these exotic structures weren't just lab curiosities, but cosmic phenomena woven into the fabric of dark matter. The connection might seem abstract at first, but the possibilities are electrifying. If dark matter interacts with time crystals, or even exists as a time crystalline phase, it could explain why it's so uniformly distributed across the cosmos. Picture a galactic halo not as a cloud of particles, but as a dynamic, time-repeating lattice, its structure echoing forward and backward in time like ripples in a pond. This rhythmic behavior might leave faint signatures in the way galaxies rotate, or in the way dark matter's gravitational influence appears to subtly shift over cosmic epochs. Scientists are already exploring how time crystals could bridge gaps in our understanding. In certain quantum theories, dark matter particles might form collective states that behave like time crystals, locking into patterns that persist across billions of years. These patterns could act as cosmic metronomes, stabilizing dark matter halos in ways that particle-based models can't easily explain. Some researchers even speculate that time crystals could mediate interactions between dark matter and ordinary matter, not through forces we know, but through the very fabric of time's structure. The implications stretch beyond astrophysics. If dark matter has time crystalline properties, it could mean that time itself plays a more active role in the universe's hidden architecture. The arrow of time, entropy, even the flow of causality, these might not be fixed backgrounds but dynamic elements shaped by dark matter's rhythmic dance. Experiments with lab-grown time crystals are already hinting at how such systems could store and process information in ways that defy classical physics. Could dark matter be doing something similar on a galactic scale? Of course, skepticism remains. Time crystals are still a young field, and scaling their behavior up to cosmic proportions stretches current theories to the limit. Yet the mere possibility forces us to reconsider dark matter not just as a substance, but as a process, a living, evolving phenomenon that might be rewriting the rules of time itself. Whether this theory holds up or not, it's a dazzling reminder that the universe's greatest mysteries might not just be hidden in space, but in the very ticking of the cosmic clock. At temperatures colder than the void between galaxies, a strange transformation can occur, particles losing their individuality to merge into a single quantum entity. This is the eerie world of Bose-Einstein condensates, a state of matter so bizarre it defies everyday intuition. And if dark matter behaves this way, it could rewrite our understanding of how galaxies hold their shape. Picture a cosmic ballet where trillions of particles move in perfect unison, not as a crowd but as a single wave. In a Bose-Einstein condensate, quantum rules dominate, allowing particles to overlap and synchronize like a perfectly tuned choir. If dark matter exists in this state, it wouldn't clump like sand or flow like a liquid. It would spread as a coherent quantum field, its gravitational pull emerging from the collective hum of this invisible chorus. This could explain why dark matter halos around galaxies appear so smooth and evenly distributed, lacking the granularity we'd expect from individual particles. The evidence might already be hiding in plain sight. Dwarf galaxies with their oddly diffuse dark matter profiles could be cosmic petri dishes for this phenomenon. Their low gravity and sparse stars might preserve the delicate conditions needed for dark matter to remain in this quantum state, like frost lingering in shadowed valleys. Even the mysterious core cusp problem, where galaxy centers show less dark matter density than predicted, could find an elegant solution. A Bose-Einstein condensate would naturally resist collapsing into sharp peaks, preferring instead to distribute itself evenly, like mist settling over a lake. Creating such a condensate in the lab requires temperatures within a whisper of absolute zero, yet the universe itself might be the ultimate refrigerator. In the vast, near-empty tracks between galaxies, dark matter could have cooled over billions of years into this quantum phase. Some theories even suggest that the condensate formed spontaneously in the early universe, when temperatures plummeted after the Big Bang's searing heat. If true, every galaxy today might be cradled in a relic of that primordial chill, a quantum fog older than starlight. The implications ripple beyond astrophysics. If dark matter is a Bose-Einstein condensate, it could interact with itself in ways that leave ghostly fingerprints. Collisions between galaxies might not scatter dark matter chaotically, but create interference patterns, ripples in the quantum fabric of spacetime itself. Detectors tuned to gravitational waves could one day catch these subtle tremors, like listening for the faintest notes in a cosmic symphony. Critics argue that maintaining such a fragile state across cosmic distances seems improbable. Yet nature has a habit of preserving the improbable when quantum mechanics takes the stage. Superconductivity, superfluidity, even the stability of atoms themselves, all rely on collective quantum behaviors that persist against the odds. If dark matter dances to the same tune, the universe's greatest mystery might not be a missing particle, but a quantum performance we're only beginning to hear. And in that realization, the cosmos grows stranger and more wondrous than we ever dreamed. What if gravity isn't a fundamental force at all but an illusion, a side effect of something far deeper happening at the quantum level? This is the jaw-dropping premise of emergent gravity, a theory so radical it doesn't just tweak our understanding of dark matter, it threatens to erase the concept entirely. Picture the universe not as a stage where gravity and matter perform a carefully choreographed dance, but as a vast, swirling information network where gravity emerges from the interactions of countless tiny building blocks, like the collective buzz of a beehive creating the illusion of a single, intelligent hum. The idea traces back to an astonishing observation about black holes. In the 1970s, physicist Jacob Bekenstein discovered that a black hole's entropy, a measure of its hidden information, is proportional to its surface area, not its volume. This hinted that reality might be more like a hologram, with the true workings of physics playing out on a hidden, lower-dimensional surface. Building on this, physicist Eric Verland proposed in 2010 that gravity isn't a fundamental force like electromagnetism, but an entropic force, a kind of statistical tendency for systems to evolve toward disorder, like how heat naturally spreads in a room. In this view, the gravitational pull we feel from galaxies isn't due to invisible matter, but to the way information is distributed and scrambled across the cosmic horizon. The implications are staggering. If gravity emerges from quantum information, the need for dark matter vanishes. The extra tug we attribute to invisible mass could simply be the universe's way of balancing its books, a cosmic accounting glitch where our equations fail to capture the true, information-based nature of reality. Imagine a galaxy's rotation curve not as evidence of missing matter, but as a signature of this deeper holographic process. It's like realizing the mysterious hand moving a Ouija board's planchette was just the collective, unconscious twitches of the players all along. But can this theory survive contact with real-world observations? Surprisingly, it holds up in some unexpected places. Emergent gravity accurately predicts the motion of stars in over 100 galaxies without invoking dark matter, a feat that's either a cosmic coincidence or a sign we're onto something profound. It also offers an elegant explanation for the tight correlation between visible matter and gravitational effects, something particle-based dark matter models struggle with. Even the infamous bullet cluster, often hailed as definitive proof of dark matter's existence, might not be a deal-breaker. Emergent gravity could explain its unusual mass distribution through the way information reorganizes during colossal collisions. Yet challenges remain. Emergent gravity struggles to explain the cosmic microwave background's intricate patterns, which align neatly with standard dark matter models. And without a complete theory linking quantum information to large-scale gravity, some dismiss it as a mathematical curiosity rather than a revolution. But revolutions in physics often start exactly this way, with an idea so audacious it's initially met with skepticism, only to later rewrite the textbooks. Whether emergent gravity ultimately triumphs or fades, it forces us to confront a humbling possibility that our hunt for dark matter might be a grand misdirection, a cosmic wild goose chase obscuring a deeper truth. The universe has never been shy about upending our assumptions, and if gravity truly emerges from the hum of quantum information, then the cosmos isn't just stranger than we imagine. It's stranger than we can imagine, with every galaxy, every star, every atom humming along to a hidden code we're only beginning to decipher. From ghostly particles whispering through dimensions to cosmic holograms rewriting reality itself, the quest to unravel dark matter has stretched human imagination to its limits. These 20 theories aren't just scientific speculation. They're a testament to our relentless curiosity, our refusal to accept that the universe's greatest mysteries might remain forever out of reach. Whether dark matter turns out to be WIMP, Axions, or something beyond our wildest conjectures, each idea has already reshaped how we see the cosmos, proving that sometimes the journey of discovery is as thrilling as the destination. Think about what these theories represent. They're not just equations on a chalkboard, they're bridges between the known and the unknown, daring leaps into the darkness armed with nothing but math and imagination. The fact that we can even conceive of primordial black holes born in the Big Bang's first moments, or quantum fluids humming through galaxies, speaks to something extraordinary about the human mind. We're pattern seekers, puzzle solvers, forever stitching together the fabric of understanding one thread at a time. And let's not forget, this story isn't over. Every null result, every unexplained anomaly, every flicker of data that doesn't fit the mold is a clue waiting to be deciphered. Maybe the answer lies in a lab buried deep underground, where a detector finally catches the faintest tremor of a WIMP. Or perhaps it's hiding in the distortion of starlight around a distant galaxy, whispering the secrets of emergent gravity. The cosmos has a way of surprising us, of revealing truths more fantastical than fiction. So what's next? That's the beauty of science. It's a collective adventure, and you're part of it. Maybe one of these theories sparked your curiosity, or maybe you've got a wild idea of your own. The comment section is your launchpad. Tell us which concept blew your mind, or share your take on the dark matter puzzle. And if you're hungry for more cosmic mysteries, hit that subscribe button. The universe isn't done with us yet. Together, we'll keep peeling back the layers of reality, one revelation at a time, because in the end, the greatest discoveries begin with a simple question.